Hello, thanks for reviewing this paper for generalized non-adaptive group testing. This is a short video to summarize the results and techniques in this paper. The group testing problem considers identifying a small defective group called D from a large population called N. The problem is motivated by something practical like pandemics. We usually do pooled tests to minimize the test times we need. For example, let's say that one person from an 8 people group is infected with COVID-19. To save regions, we first test the mixture of samples from half of them. If the outcome is positive, we will test on a quarter from the half. And if it's negative, we can say that the diseased person is in the other half, and we will test a quarter from the other half. And we do that once again, then we can identify the diseased people. Here, the mixture of samples is called test pool. We can see that the method only requires 3 tests, while testing them one by one require 8 tests. But in this scenario, we must wait for the result of the first test in order to design the next one, which takes much more time. So we consider non-adaptive group testing. It means that all test pools would be decided before we do the tests. For example, we can number the 8 people by the number from 0 to 7. And we can write them in the binary form. So in the first test, we test the item whose first digit is 1. And in the second test, we can test the item whose second digit is 1. And in the third test, we can test the items whose third digit is 1. Then we can parallelly do the 3 tests, and the outcome shows the diseased person. For example, if the outcome is positive, negative, positive, then we know that the diseased person is 101, which means he is the 5th person. So this allows us to do testing without waiting for others' test outcome, which can minimize the time we spend on the testing. Furthermore, we consider generalized group testing. So what does generalized mean? Let's first talk about the classical one. The classical group testing says that if there exists at least one defective item in the test pool, the test outcome would be positive. Otherwise, if all people are non-defective, the outcome would be negative. But due to some chemical constraints, we think that the outcome is not always that so accurate. So we consider generalized group testing. That is to say, we will not always get a certain outcome, but the outcome follows the Bernoulli distribution. Generally, the more defectives in one pool, the outcome is more likely to be positive. Okay, so let me give you an example. So in this figure 2, when number of defectives in the pool is less than d over 3, the outcome is definitely negative. When the number is larger than d over 2, the outcome is definitely positive. When it is between d over 3 and d over 2, the probability that we get a positive outcome increase linearly. The relationship between number of defectives and positive probability is defined as test function f. And in this paper, we offer a testing method for nearly all test functions. So in all group testing, d log n is known as a lower bound for test times, regardless of the testing method you choose. And our method needs no more than d square log n tests for all functions, while for some specific sensitive functions, our method requires d log n test, which is near optimal. So the introduction parts present all those works in similar areas and the results they obtain. And actually our result is pretty good among them. Then let's turn to the problem formulation part. Here is a set capital N of n items, where each item is defective with probability P, and there are expected to have D defectives, which formulate the subset capital D. Our aim is to identify capital D, and our identification is called D hat. Due to some probability issue, we cannot always guarantee that we obtain the correct D, but we can keep our error to be smaller than some given number called epsilon, which scales as n to the minus delta. So in our testing, the size of test pool is really important. We will choose a specific parameter S according to the test function. And then each test pool is designed by randomly choosing S plus 1 items from the set N. Namely, the pool size is fixed to S plus 1. Then let me introduce more parameters to you. So the first one is the test positivity probability. We focus on one item called I. Say that it is included in one pool. So from his viewpoint, the other items are randomly drawn, which means that they contribute the same number of defectives. So when I is defective, there would be expected to have one more defective in the pool, comparing with a case when it is non-defective. Hence, we will identify the items that are involved in more positive outcome tests as defective, while others as non-defective. So here we define P minus S as the probability that the outcome is positive when I is non-defective and there are S other items. So here the minus stands for I is non-defective. It can be computed by calculating the probability that there are J defectives in the S items and the probability of positive outcome when given J defectives, which is Fj. And adding up all positive J's, we obtain the test positivity probability. And when I is defective, the P plus minus can be computed similarly. While the only difference is that there are J plus 1 items totally, since the added one is I itself. Then the item test sensitivity is defined as the difference between P plus S and P minus S. So intuitively, we try to make the delta larger in order to easier identify the items with smaller error. And minimal test sensitivity guarantees a tempered positive or negative probability. And we will discuss more on it later. Then is the test participation parameter, which is a lower bound of tests that one item must take. And finally, we claim that this number of tests, capital T, is enough to solve the problem. Okay, let's back up a little bit. So how to choose S? We offer two theorems to do that. The first theorem is quite straightforward. We first find L1 and U1 satisfy this equation, and then we can find K1 such that Fk1 has the largest increment in the region of L1 and U1. Then we can choose S as K1 over P. So the equation 5 restricts the value of P main, and the largest increment restricts the value of delta. For example, for some function shown in figure 1, we will choose S1 as 4 over P. Then let's go to theorem 2. The result we obtain in theorem 2 is overall better than the result in theorem 1, but we cannot always offer a direct way of choosing S. While we can only prove that such an S exists, but in theorem 1, we can always offer an exact answer of choosing it. So we provide two theorems. And first, we can divide the theorem into two cases. The first case says that there exist some regions that has sufficiently large increment, which means fk2 plus 1 minus fk2 is instead of 1. Then we can directly choose S2A to be K2 over P. This case is kind of matching with the theorem 1. For example, in figure 1, we also choose S2 to be 4 over P. And then the case 2 stands for the functions that increase relatively slowly. We claim that there exists some function hd such that when x is smaller than hd, fx is in small o of 1, while when x is larger than hd, fx is in set of 1. Then we can find c in set of hd such that fc equals to w, where w is in set of 1. Then, similar as above, we find L2 and U2 that satisfy this inequality. After that, although we cannot give the exact way to choose x, we can claim that we can find some S2B in L2 over P and U2 over P, which satisfies the equation 24. Okay, let me give you an example. So we consider the function given in equation 14, which is also shown in figure 2. Since we can see that this is a case, the function increases slowly, and we have hd equals to d here. Then we can choose c equals to d over 2, since fd over 2 equals to 1. And accordingly, we can compute that L2 equals to 7d over 18 and U2 equals to 8d over 18. Then we can choose S2B as 5d over 12p, which is the midpoint of L2 over P and U2 over P. Now let's go to the decoding part. We first say that each item should be involved in at least m tests with high probability. Otherwise, it will be directly identified as non-defective. And for the items that takes at least m tests, we will randomly choose m tests from all and count the positive ones in the m tests, denoted by m plus. then m plus over m is then if m plus over m is smaller than this value, it will be identified as non-defective, while when it is larger than this value, it will be identified as defective. The bound here is a value, it is a value between p minus s and p plus s, which is considered to be the best bound. And finally, here comes lemma 1, which is which is the most important lemma, says that the above test design can identify the defectives with error probability smaller than epsilon. So generally speaking, the two theorems tell you how to choose how to choose S in order to optimize delta S and P min S. And lemma 1 proves that such a choice can do the things we want. Okay, now let's dive into the two theorems. In theorem 1, we directly choose L1, U1, and S1 as above says. And we have lemma 2 says that a choice can be bound can bound delta and p min like this. Hence, using equation 19 here, we can compute that t equals to this value, and we notice that t is in d cubed log n. And in theorem 2, so for case 1, lemma 3 says that we can bound the two parameters like this. And then we can bound t in this way, and t is in d log n. And for case 2, lemma 4 proves the existence of S2B satisfies these conditions. And then t should be like this, which is in d square log n. Overall, t should be in d log n for case 1 and be in d square log n in case 2. Then let's go to the proof part. For lemma 1, we first bound the probability that each item participates in at least m tests. We know that the probability should be smaller than 1 minus epsilon over 2. And then we compute the probability that all items are correctly identified. It is divided into two parts. One is false defective and the other one is false non-defective. So then the lemma 7 here is a lemma used in the process, and it can be easily proved. And we can bound the probabilities of both false negative and false defective and false non-defective are smaller than epsilon over 2n. So the probability is that when the items take more than m tests, the probability of correct identification is larger than 1 minus epsilon over 2. Finally, the overall correct probability is larger than 1 minus epsilon, and lemma 1 is proved. Then is a proof of lemma 2. To be mentioned that most of the proof in the appendix is tail bounds. Lemma 2 makes use of lemmas 8, 9, and 10. Lemma 8 helps us to bound this quantity. which stands for the probability that there are exactly ds defectives in ds over p items. And lemma 9 bounds the probability that there are less than ds defectives in the ds over p items. And then the lemma 10 bounds the probability that there are more than ds defectives in the ds over p items. Okay, so combining all of them, we can prove that delta S is larger than this value, and P mean is larger than 1 over 75, which is the result that we desire. Then the proof of lemma 3 is similar to lemma 2. So using lemma 7, 8, and 9, and 10, we can similarly bound delta and p mean in this way, which is the result that we want. And then it's a difficult part, lemma 4. We first introduce another lemma called lemma 11. It keeps ds fixed and s changing. So it helps us to bound the sum of delta s from L2 over P to U2 over P. So we will add up all of the deltas, and we use summation transformation to get equation 74. And lemma 10 help us to bound 74 to 75. And then we can say that there must exist a S2B such that delta S2B is larger than the average delta. And the answer is what we desire. Then we use lemma 9 and 10 similarly, and we can bound P mean in this way. So hence the proof of lemma 4 is completed. The last lemma we need to prove is lemma 11. In this proof, we first change the scenario into another one. So it can help you better understanding it. So we can easily obtain 80 from the given scenario. And then using monotonicity, we obtain equation 82 and 83, which changes the original summation into a summation that is easier to bound. We can compute the ratio between two adjacent summations, as in 84 and 88. Then we can change it into a geometric series. Hence, we can compute that both of them are larger than 1 over 14. And combining all the above inequalities, we can bound the original summation like this. And hence, the proof of lemma 11 is completed. Okay, now all the proof is completed. So finally, let's go to the simulation part. Okay, here it is. We run some programs to verify our test design in Theorem 2. Firstly, we input the basic parameters like N, D, F, and T, and we will do testing as above. So the testing part is similar, but the decoding part is a little bit different. For easier implement, to identify an item I, we directly consider all the tests that I participates, denoted as T. Instead of setting an lower bound M on T and choose M from T for identification. So anyway, we believe that this small change would have small influence on the outcome, and and then we will count the number of positive tests within the T test denoted by T plus. And we compare our identification with the original state, and then we can identify I by the ratio between T plus and T. Then we can compare our identification with the original status. If they are the same, we say that our test success. Otherwise, we say that it fails. And we use waterfall plot and heat map to visualize our outcome. First, for case 1, we will first set a value interval of t, which is 5d log n and 25d log n. Then we take 100 numbers from the interval to be the value of t, and the pool size parameter is s is chosen as 4n over d. For the waterfall plot, we set n to be 6,000 and d to be 30. And we repeat one case for 1,000 times. Then we obtain figure 3. We obtain figure 3 here. And we also obtain that the 99% point is around 19.8 d log n. Here, the 99% point is our estimation of the smallest t that satisfies the correct probability is larger than 99%, or to say that epsilon is smaller than 1%. Then for the heat map, we make n fixed and d changing, or makes n changing and d fixed. And we use the depth of darkness to represent the failure rate. The lighter one pixel is, the success probability is larger. And we can also find the average 99% point. So then for the case 2 in theorem 2, we will set the interval as d square log n over 10 and 8d square log n over 5. And we obtain similar results for waterfall graphs and waterfall plot and the heat maps. By the way, due to time limitation, we take less testing time on case 2 because it takes too long to run the program. So the error may be a little bit significant, but we can still see the overall trend of changing. And we may offer more data and more precise results in our further updates. Okay, my speech ends here. Thanks for your listening and bye-bye.